Now for some time I've been looking for a simple way to add a choke to a waveguide feed. In particular I wanted to make one just to add to a satellite dish, for instance, because I get a lot of questions whether you can add one of these to a satellite dish. This is the size of Cantenna that I normally sell. This is made from a toilet roll brush holder. This one's mine from here in the lab, so it's a little bit beat up. But something like this is just too long to use with a satellite dish, and you know, you can make one for a satellite dish basically out of a baked bean can, and you only want it to be around as long of the length of a can of baked beans. Now you do as a minimum need 73 millimeters diameter on your tin, so that's something to watch out for. Anything less than 73 millimeters isn't going to work for you. That's the minimum diameter of the Cantenna that you can use for 2.4 gigahertz. But a really narrow one like this one here is ideal for a satellite dish, along with the smaller length. Now, adding a waveguide choke like this doesn't necessarily make it any more powerful, but what it does do is eliminate any side lobes. It cuts down on that noise, and although you know, the signal strength from one of these would look pretty similar to one without a choke on the sides, because you're cutting down on that noise, it's a lot faster for an internet connection, because you're not constantly sending back and forth for repeat packets, because you've got corrupted data coming down the line. But a waveguide choke, yeah, it eliminates all the noise, cleaner signal, so then you get a faster internet connection. Now, why you don't normally see these in the amateur side of things for Wi-Fi, for instance, is because to make a choke like this, it's normally milled out of one piece of aluminium block, and it's really expensive. And the smaller ones, say the 6, 8, 10 gigahertz little waveguide, you can get for test setups and testing in general on the bench, they're normally milled out of a piece of brass, so they're even more expensive. They may be smaller, but you know, the price doesn't go down. Now, using these cookie cutters that I saw on a recent episode of Tested, as soon as I saw these, I thought, you know, maybe I could use those. So what I'm going to do in this video is just show you how this is the first attempt at soldering them all up. I'm going to do on the bench now, because unfortunately I've ordered a few of these. These are the first ones to turn up. Stainless steel isn't always solderable to. You can't always solder to stainless steel. Now, when I first started making the Cantennas out of toilet brush holders here, I could solder to them, and I would often solder the SMA connector directly onto the tube, but I haven't been able to solder onto any of the toilet brush holders that I've you know, been getting in recent years. They're still stainless steel, but they're just a different kind of stainless steel. I mean, it's an entire subject on its own, but these are not magnetic. They do claim to be stainless steel, but they just will not take any solder. So what I'm going to try and do is solder them to this piece of galvanized steel that I've cleaned off here. The steel will take the solder really well, and I'm going to try to lock these in place when I melt the solder. So instead of the solder adhering to the rings itself, how you would normally do when soldering something, I'm going to try to lock it all in place so the solder is you know, got a good connection to the steel, and then lock it in with these little ridges that are around these cookie cutters. So it may work, it may not. Now, sometimes you get an idea and it doesn't quite work out how you planned. I wasn't able to solder these by locking them in at all. It just virtually fell to pieces. So what I've done, I've removed them. I've cleaned up all the edges here that are going to make contact. I'm now going to use some single-sided PCB to connect to these. So I've cleaned up all the edges, and I'm going to have a go at using some of this wire glue. So it's electrically conductive, so hopefully we'll get contact between the rings here, the stainless steel rings, and the ground plane of the PCB board. You have to leave this for quite some time. It says to leave it for 24 hours. I've never used this before, and you know, different things like this do have an application over solder sometimes, especially if you can't solder to something like this stainless steel. I picked this up when Maplin's was closing down. I picked up 2 packets of these, only paid about 80p each for them. Never used them, so I'm going to give this a go now. Hopefully it'll sort out the problem for us, but from what I've seen online, this isn't particularly strong stuff, so I'm going to use the wire glue first, and then I'm going to you know, strengthen that bond by using some something like epoxy, something like that, over the top of this stuff, just to hold it in place and make it a lot more permanent. A few videos on YouTube showing how to use this are all to do with soldering wires, and a lot of the comments say you're better off using solder, and I agree with those comments. I would never use this when you can use solder over something like this, but for this application it might work out well, connecting it to the PCB here, so we'll give that a go. So I'm going to start with the smallest ring first and basically work my way out. And of course I've cleaned the PCB as well with some wire wool and given everything a clean with some isopropanol, just to get rid of any grease or dirt. So that looks okay, so I'm just going to work my way out. So I've got them all in place, and what I'm going to do is put a weight on this, put it to one side out of the way, and just let it dry naturally for the 24 hours that the instructions say to wait. I've seen people on YouTube use a hairdryer to speed this up, but I'm just going to leave it to one side and we'll see what it's like tomorrow. So here we are then, the following day, and it's cured overnight. Now it does say in the instructions to this, if you want a really you know, secure fix with the solder glue, is to use some super glue on it as well. Now I have gone around the sides with the super glue, around the outer edge here and the inner edge in here, with a good liberal amount of super glue there, just because what I'm going to do is I'm not going to use epoxy in between here as I first thought I would. What I'm going to use is a polyurethane based fiberglass resin, and you get a bit more work time out of it, and it's a little bit runnier as well, just to pour it down in between here, just to make sure this is nice and affixed to the PCB, because it doesn't fill me with confidence using the solder glue and super glue. I think the resin's going to do a really good job of holding it down, but we have got good continuity between all these rings here, so you know, the solder glue is doing its job. So this is the resin that I use. I've used this for many years now. It's quite easy to work with, and it doesn't smell as bad as some of the other resins that I've used in the past. Funnily enough, I've just ordered this off of eBay from a seller that I bought for previously, and normally you get a couple of rubber gloves in with the kit as well, but for some reason they're not included this time. So I've made this little lip here, and I'm just going to pour it in between the gaps. So it's on there, it's really solid on there now. I don't think it's going to come off anytime soon, and I did end up leaving this overnight because I went off and did something else, but the most important thing is we've still got conductivity through all the rings, and that's what I was hoping for with the solder glue. So what I'm going to do now is take this over to the bandsaw, cut away all this excess PCB around here. I can just use the outer ring as a guide to cut round there, and finish it off with a little bit of sandpaper just to tidy it up a little bit more. And then I'm going to have to cut the centre out here so we can fit it over the can. So the choke is finished now, and I've started to do some work on the can. I've cut away the lip from the entrance of the can here, so it's nice and smooth on the inside now. Roughed up the can as well, as you can see, with a bit of sandpaper, just so we've got good electrical conductivity between the choke and the can, so they are connected now electrically. I've just checked that with the continuity meter. But what I'm looking at doing now is the feed, and because this choke wants to be positioned a minimum of a quarter wavelength. I mean, we can play around with that in the future and see if we can improve that, but it seems to be a quarter wavelength from the entrance of the waveguide. That's going to be a problem when it comes to putting in the SMA connector for the monopole element inside here, because it's right on top of where I need to drill in. With this particular dimensions of this can, it sits quite near the front because it's a short can and it's only about 75 millimeters in diameter. So I'm going to do something a little bit different with this one, and I'm going to come in the back and then run a feed line on the inside of the can, and then have the little monopole coming up there. So let me explain what I'm going to do with that, because it is a little bit different, and I haven't done anything like that before on this channel. So I'm still going to use one of these bulkhead SMA connectors that I use on the big Cantennas, but I'm going to be connecting to it a little bit differently. I've got a length of coax here. Let me pull this out of here. You can see I've got my little pin on there, and I've stripped away the outer braid, and I'm just keeping this outer braid here as a insulator to make sure that we don't basically that it doesn't start radiating before I need it to. So at the moment it's a signal line, and that comes down here, and it only starts radiating as an antenna when you strip the coax back. So this piece of coax here, as soon as I strip back the outer braid, then this becomes an antenna. Until you do that, then this just stays as a transmission line. And as for the ground, we're going to get the ground connection to the can itself through the the bulkhead SMA connector being screwed onto the can, so we don't have to worry about that too much. We're just feeding our signal straight along this coax here, and then when we're ready to turn it into an antenna, we strip away the coax and then expose that inner core of the signal on the coax there. Now I could, instead of using one of these, use one of these bulkhead SMA connectors. Now there's no problem with doing that, of course, but to connect an alpha card here, then we're going to have to use something else to connect in between this SMA connector here and the SMA connector on the alpha card. I don't like doing that if I don't have to, because you're just adding loss to the system then when you don't really need it. It's the same thing as, if you don't need a long run of coax, then I would stay away from that and have possibly a longer USB cable. That way you're not getting any loss. So it's going to be a little bit differently. Connect this on the end of the can and then run the coax along the base of the can here, and then have it coming up to create the antenna. Now I'll put measurements in the description for a range of different diameter cans where you need to position the probe, but basically for this can it needs to be 81 millimeters away from the base of the can. So I'm just measuring this length of coax here on the ruler, and I'm going to put a mark at 81 millimeters, and what I'm going to do is strip away the outer braid of this, just to so we've just got the signal wire, and then put a 90-degree bend up just to form the element. So round about 81 millimeters. So I've got the coax laid in the can now, and because I've already pre-tinned around the end of the outer braid of the coax down here, I'm just going to lay some tin down onto this side wall of the can here. Then I can just go in with my soldering iron and then get all that to flow and permanently fix this down to the side wall of the can. So you can see I've put some epoxy putty down in there just to cover up where we've soldered it to the soldered the coax to the side of the can, and I've put some brass tubing over the top of the coax. That's measured at 30.9 millimeters. That measurement works well to stay resonant at 2.4 gigahertz with this size of can and this diameter. I've done many videos in the past showing that how the diameter of the can and the length of the can have an impact on the driven element. It's not just as straightforward as working out a quarter wavelength, but you can see I've got a little bit of the coax sticking out of the top there. So what I'm going to do is solder it in from the top, and then I'm going to clean away any excess just to make sure that this still is 3.9 millimeters. But that's basically about it finished. So I'm thinking about giving this a test, and this time I'm not going to just scan for wireless networks. What I'm going to do is connect to my wireless network in the house, not here in the lab because I have got an access point here in the lab, but this with a small satellite dish should pick up the access point in the house. And because we're looking at here adding the choke to keep the noise down, this with the choke, this can with the choke should be a lot quicker, a lot more megabits per second than one without the choke. At least that's the theory anyway, and that's what I'm hoping for. Okay, so let's give this a go then, see what kind of speeds we get from here in the lab. Normally I get around 30 megabytes a second. So it's a little bit low, creeping up though. So around 30, which is what I kind of expect. Upload speed almost 10. So 30 and almost 10 for upload speed. So let's give it a test now with the waveguide choke. So let's give it a second test with the choke then. So big jump to start off with. So a big difference there in upload and download speed. Definitely a difference. So here is the finished Cantenna with its paint on then, and as you saw in that test, there really is a difference between the internet speeds. Now, testing this on gain only, you're not really going to see any significant increase in gain. I mean, adding the choke around here is not going to do that for you. But as you saw in the test with the internet speed, it was significantly faster than the can with no choke, and that's the only difference between those two cans, just the choke around this one. And I did that test quite a few times as well, and each time this one always come out faster. So it's certainly doing the job of making everything a little bit less noisy, and of course not as much noise, not as much corrupted packets. It doesn't have to request them again after they're being corrupted, so you get a faster internet connection. Now, when it comes to using a satellite dish for a Wi-Fi connection, most people, you see, use the smaller satellite dishes. Like in the UK here we have the Sky one, and I know in the States you've got the direct TV dishes, and they're quite a small dish. And something this big with this kind of large diameter choke, I think what would probably happen with a small dish is this would block a little bit of the signals coming in, because it's you know, much wider in diameter, and a smaller one like this would work a lot better. And again, I've done some tests off camera with this one, and you know, just adding three of the rings on this smaller one again increases the speed. It's really quite amazing how I mean, I didn't really think I'd be able to show you it in the real world, if you will, but there's certainly a speed difference by adding the choke around here, so it's definitely doing its job, as I said. But a smaller one like this is probably going to do a lot better on a much smaller dish. You know, with the smaller profile footprint of this, not blocking so much of the signal coming into the dish. But if you've got a bigger dish, like you know, probably just under a metre across, I mean, you can pick them up off eBay. I've seen them for something like £20 and a £5 delivery. Then yeah, this is going to work out a lot better for you. So for smaller dishes, something like this, and bigger dishes and upwards, this is definitely going to do the job. And as I said, I am pretty amazed at the difference in the speed test. And this has come about by some research I've been doing, because I'm trying to put together a radio telescope, and that's going to be my new hobby for the next few years, putting together a radio telescope. And I was looking at noise and how to reduce noise on a thing like that, and this is something that works really well for that application. But also, you know, on a Wi-Fi setup with a satellite dish, also works really well on that application as well. And the solder glue really did save the day. This is a really good fit for this stuff to use, you know, when you can't use normal solder. Something like this to get the connection, the ground connection between all of these rings here and the PCB board at the back. So a really good fit for the solder glue. And as always, when I'm making one of these videos, I always make a few of them off camera as I'm going along shooting the video. So what I'm going to be doing is giving away one of the larger ones and one of the smaller ones away to the Patreons over on the Patreon channel. So if you want a chance of getting hold of one of these, then you know, feel free to support me on Patreon. So as always, I hope you enjoyed this video, and you know, you've learnt something from this. And if you have a go at making your own, then please let us know in the comments how you get on, especially if you have a go with the solder glue like I did. And if you did enjoy it, please give it a thumbs up, and hopefully you'll join me on the next one.